Okay, so this is a video of just another example of an interaction diagram. This time there'll be significantly more interactions here, but now we have block table string. So I'm going to start with uh, labeling the objects in circles. So we have B for block, T for table, entire Earth, EE, and over here I'm going to do S for string, and we'll see how the string is actually interesting in this one. But it is an object, so we want to include it here. And so we'll start between block and string. There's definitely going to be a tension force between those two. It's at constant velocity, so this tells us that forces are going to have to balance, which means the only way this thing's going at constant velocity is if there is a frictional force. So between the block and the table, there's going to be two interactions, and one of them will be a normal force, one of them will be a frictional force. Between the block and the entire Earth, we have gravitational interaction, and again I use dotted lines to indicate long-range forces. Likewise, we're going to have a gravitational interaction between the table and the entire Earth. And there may be a gravitational interaction between the Earth and the string, but I'm going to assume that the string is just so light that we can ignore that force of gravity. Essentially, we're making the massless string approximation here. Okay, so now I'm going to move on to the force diagrams, and I'm going to draw force diagrams for all four of these. On the worksheet, it's up to you. You pick two objects or groups of objects, and you draw the force diagram for them. Okay, so to start with, let's do a simpler one. Let's look at the block. So we'll use this block. We've got four forces: gravity, friction, normal, tension. Tension force on the block by the string is this way, and again we can use our abbreviations. Tension force on block, comma, by string. Normal force on block by table. Gravitational force on block by entire Earth. And frictional force on block by table. Those are the four, 1, 2, 3, 4 interactions on the block. And with this constant velocity thing, I know the forces have to balance. So this upwards force is equal to this downwards force, and this leftward force there is equal to that rightward force there. You should draw the arrows the same length for vectors that are equal size, but these hash marks can help us make sense of the diagram if we're not, drawing to scale, just sketching. For the table, actually, let's do the entire Earth, because that reveals some problems with my interaction diagram, which this force diagram will make clear. So if I look at the entire Earth, I have two gravitational interactions, all right, from the table and the block, and those would be upwards forces, because they'd be downwards forces like this one on the block by the Earth. So the force on the Earth would be an equal and opposite upwards force of gravity on the entire Earth by the block. And granted, that force is going to be, well, it's going to be the same size as this force of gravity on the block by the entire Earth, but the Earth is so massive that it doesn't accelerate up very quickly. And then we're also going to have an upwards gravitational force, Fg, on the entire Earth by the table. But this is problematic because the Earth, even if it were a small value, small is not good enough. The Earth doesn't accelerate up at all because the table rests on the entire Earth. So what's missing from this diagram here is a normal force. So I've got to include that, and then that would give us this downwards force, because I can't have a table that's, I can't have an entire Earth that's accelerating up, even if that number is small in this problem. So this would be normal force on the entire Earth by the table. All right, and if you didn't realize that that force is there, when we draw the force diagram for the table, it would be clear that we need kind of this upwards pointing support force. And we'll make that clearer when we draw the force diagram for the table. Okay. So let's do that next. Let's draw the force diagram for the table. So we'll do that over here. So for the table, I've got at least 4, 1, 2, 3, 4 that I need to include. So I have a frictional force on the table by the block, and this is tough to decide which way it points, except that I've already decided that it points to the left on the block. This is the other point of view of that same force, so it's the Newton's third law pair. It's got to be equal and opposite. So this would be force of friction on the table by the block. And it should kind of make sense. The block is getting pulled to the right, so friction between the block and the table would tend to try to drag the table with it to the right. We've got a normal force on the table by the block, and again, it's a little bit easier because we've decided here that that thing's going to be up on the block, so that means it's down on the table. Normal force on table by block. So we've taken care of the frictional force and the normal force. We have this normal force on the table by the, well, hold on, actually, let's just do the gravitational force first. So this here, we've got Fg on table by the entire Earth. And right now you can see the need for an upwards force. So again, we have to have this force here, otherwise our table would be accelerating down. And if you were kind of wondering about, well, then maybe the Earth could accelerate up, it's so small we can ignore it. We can't ignore the fact that the table doesn't accelerate down at all, and that's where we need this normal force, upwards normal force on the table by the entire Earth. And that's linked with this one, because those are Newton's third law pairs. They're the same interaction, the 2 points of view, equal and opposite. Like these two are linked through a third law interaction. You can see the subscripts are just reversed, and it's the same interaction. And then these two are linked through a third law pair. So if you look at our table, this is still problematic. We have a table that maybe the up and down forces can cancel out, but there's this force to the right. What is holding the table back from accelerating to the right? Well, this is where we can see that there's one other thing missing on our interaction diagram. If there's no friction between the table and the entire Earth that it rests on, and you pull this block across the top, the table would start to accelerate. So there has to be another missing force, another interaction that we can use to hold the table in place. And this would be a force of friction between the table and Earth. And so that I can add now onto this thing. Frictional force on the table by the entire Earth. Okay, and now we can see how these forces can balance out on the table. This could cancel that. And then this force here can be canceled out by these guys there. So those two added together, we can think about those canceling out that upwards normal force on the table by the Earth. Okay. If you see that there's potentially a problem with this one that's still left here, good job. Right here, we have a force on the table by the entire Earth. The other point of view would be equal and opposite on the entire Earth by the table. That means we've got this force on the table by the entire Earth, and now it's like, well, great, now our entire Earth is going to be accelerating to the right, because if the table gets pushed to the left by the Earth, then the Earth gets pushed to the right by the table. All right, and so the object we haven't drawn the force diagram for is the string, and so let's consider that one now. So we have the string, and right now we have this backwards force to the left, because the tension force on the block by the string is to the right, so the tension force back to the left on the string by the block is to the left. So tension force on the string by block. But our string moves to the right at constant velocity. And from this force diagram that we just drew for the string would be accelerating to the left. That doesn't make any sense. So we know something has to pull this string to the right, and that's kind of obvious, right? The string isn't going to go by itself this way. But what we don't know is what object is pulling it this way. I'm assuming it's somebody's hand, right, that's pulling this thing to the right, and that's what allows this to happen. Okay, so if that's really what's going on, then that fixes our Earth problem as well. So imagine somebody holding this thing, right? They would form another connection with the entire Earth down here. And so you can see how this kind of goes on and on and on, but there would be an interaction here between the person who's holding this thing and the ground. And if they're pulling it to the right, we can see eventually how we could end up with this force of friction back here on the entire Earth by the person, right? But um, this is just to show you how these interaction diagrams can lead to conclusions that are not obvious if we're careful with them. But realize that, for a problem like this interaction diagram is not really necessary. Really, we would be focused on making sure that this force diagram is correct, because it's probably the block that we're trying to explain. This is really a worksheet to practice with these interaction diagrams, so that when we do need them to make difficult decisions, like what are all the forces acting on the Earth, or if the question starts asking about frictional forces on the table, we're kind of prepared with the tools that we'll need to figure that stuff out correctly. Okay, that's the second example. Use the rest of the time to work on the first 7 problems of worksheet 1 for Unit 4, and we'll be whiteboarding those when I get back tomorrow. All right, bye-bye.